All right, everybody, welcome back. Buckle up because today we're taking a deep dive into some pretty wild physics. We're talking about tantum gravity. Yeah, you heard that right. We've got a whole pile of research papers and notes here ready to untangle this mind-bending concept. And it all starts with this thing called the Bronstein cube. Ever heard of it?
Not exactly a common topic at the dinner table.
Right.
Basically, think of the Bronstein cube as like a map, but instead of countries and continents, it maps out different theories of gravity.
Okay, a map of gravity theories. Interesting. But what are we actually mapping here? Like, what are the landmarks on this map?
Imagine an actual cube, like you hold in your hand. Each side of the cube represents a fundamental constant in physics.
Yeah.
Things like Newton's constant, which basically tells us how strong gravity is. And then there's Planck's constant, which has to do with the quantum world. And of course, the speed of light, which is, well, the speed limit of the universe.
Gotcha. So each side of the cube is like a dial for a different constant. So what's happening inside the cube then?
That's where the fun begins. When you move around inside the cube, you're essentially changing the values of those constants. And depending on where you land, you end up in a different theory of gravity.
So like one corner of the cube might be good old Newtonian gravity, and then you scoot over to another corner and boom, you're in Einstein's general relativity.
Exactly. And there are other spots on the cube representing even more exotic theories, like quantum field theory, but in curved space-time. Really wild stuff.
I can imagine. So where does tantum gravity fit into all of this? What makes this corner of the cube so special?
It's all in the name, actually. Tantum comes from Latin and means that much. It's kind of a play on the word quantum, because in tantum gravity, quantum effects are amplified. They're enormous.
Huge quantum effects. Okay, I'm intrigued. But how do we even get to this tantum gravity corner? Do we need a special compass or something?
Think of it as a triple scaling limit.
Right.
Essentially, we're cranking up Planck's constant, that's our quantum dial, to infinity, and at the same time, we're turning down both Newton's constant and the speed of light towards zero.
Whoa, wait a minute. Turning down the speed of light. Doesn't that mean nothing can move?
It's not that nothing moves, it's more like things get really, really strange. When the speed of light vanishes like that, it's called the Corollian limit. And that's one of the things that makes tantum gravity so unique.
Okay, so in this tantum gravity corner, we've got maximum quantum weirdness and light basically crawling at a snail's pace, or not moving at all. What happens to gravity itself in this scenario? Does it just disappear?
That's where things get even more interesting. Even with the speed of light basically gone, tantum gravity still has black holes.
Black holes, but those are all about gravity being so strong that light can't escape. How can you have a black hole if light isn't even moving?
And that's the puzzle that tantum gravity forces us to confront. In this limit, the way we define black holes needs a major rethink. We can't rely on the classic picture of an event horizon, that point of no return where light gets trapped.
So if it's not about the event horizon, how do we even define black holes in tantum gravity then?
We have to look at something much deeper, something more fundamental. Their thermodynamic properties. Things like entropy, temperature, and energy. These properties stay well-defined and finite in tantum gravity, even as the speed of light vanishes.
So instead of light being trapped, it's more about these fundamental properties that define what a black hole actually is.
You got it. And this shift in thinking actually lines up more closely with how physicists think about quantum black holes. These types of black holes evaporate over time and don't have true event horizons to begin with.
So it's like tantum gravity gives us a sneak peek into the quantum nature of black holes, even if it is through a very extreme, very abstract lens.
Right on. It's definitely pushing us to rethink our most basic assumptions about gravity and how it works when quantum mechanics is involved.
I can definitely see that. Now, I know from these papers that just getting to this point requires some serious math. The researchers are using something called the Euclidean path integral. Can you give us a breakdown of that without getting too technical?
All right, try to picture this. You're trying to find the shortest path between 2 points. But instead of just drawing a straight line, you consider all possible paths, even the really crazy, winding ones.
So instead of taking the highway, I'm taking every back road and scenic route, even if it takes me 10 times longer.
That's the idea. The path integral is a way of adding up all those possibilities, each one weighted by its probability. In physics, we use it to work out the most likely behavior of a quantum system.
Okay, so in this case, we're using it for gravity itself, trying to figure out the most probable configuration of space-time in this wild tantum gravity limit.
Right, got it. It's like saying, given these extreme conditions, what's the most likely way for gravity to act? And turns out, even in this really bizarre limit, The math still leads us back to black holes, but they're defined by their thermodynamic properties, not by their event horizons.
That's incredible. It really makes you wonder if black holes are even stranger and more fundamental than we ever thought.
It definitely challenges those classical intuitions we have about gravity. And the exciting part is, this is just the beginning. There's a lot more to explore in tandem gravity.
Well, I'm ready to dive deeper, but first, I think we all need a moment to let all of this sink in. When we come back, we'll unpack the math a bit more and look at how the researchers actually show that black hole thermodynamics still works in this extreme limit. Stick around. Okay, so tandem gravity. Quantum effects are cranked way up, the speed of light is basically zero, and black holes are all about thermodynamics, not event horizons. Now let's get into the math a bit. How are researchers actually showing that black hole thermodynamics works in this crazy limit?
Well, they actually start with a simplified model of gravity. Remember how we were talking about the Bronstein cube and all its different corners? Instead of tackling the full complexity of quantum gravity, they actually focus on a model that lives on like an edge of the cube, kind of like a two-dimensional slice of space-time.
So like taking a cross-section of the Bronstein cube, just to make the math easier to work with.
Exactly. And this simplification lets them use that Euclidean path integral we were talking about earlier to calculate things like entropy, temperature, energy. And they actually do this specifically for a Schwarzschild black hole, the simplest kind of black hole.
So they're basically saying, let's take the simplest black hole we know, put it in this simple 2D world, and then crank up the quantum dial and see what happens.
Pretty much. And even with all the simplifications, the calculations are still pretty complex. But the main takeaway is that they find the black hole's thermodynamic properties stay finite and well-defined, even in that tandem gravity limit.
Hold on, before we get too deep into those calculations, can you remind me again why they're using the Euclidean path integral? What's so special about it?
The path integral, remember, it's a way of summing up all the possible histories of a quantum system. Like, given where it starts and where it ends, what are all the ways it could possibly evolve? And each of those paths contributes to the overall probability of ending up in that final state.
Okay, right, I remember that from before. But what's the Euclidean part all about?
So in physics, we often use what's called imaginary time instead of real time in calculations. It's a mathematical trick to make things easier, kind of like using complex numbers to solve certain equations. And when you use imaginary time, you're working in what's called Euclidean space instead of the regular Minkowski spacetime.
So it's like swapping out a regular map for a special map that makes certain calculations easier to do.
Yeah, that's a good way to think about it. The Euclidean path integral is really useful for studying systems at thermal equilibrium, like our simplified black hole.
Okay, I think I'm following so far. So we've got our simplified black hole, our Euclidean path integral, our tandem gravity limit. What happens when we put it all together? What do the calculations show us?
The calculations show that even as that speed of light approaches zero, the black hole's entropy, temperature, and energy, they all stay finite, and they fit with the laws of thermodynamics.
But how is that even possible? If the speed of light is zero, shouldn't everything just freeze?
That's where the difference between classical physics and quantum physics really comes in. In classical physics, yeah, a speed of light of zero would mean everything is static. But in quantum mechanics, it's more subtle. Even with no speed of light, particles can still have energy and momentum. And these quantum fluctuations, they're what allowed the black hole to keep its thermodynamic properties.
So it's like the black hole is being held up by this kind of underlying quantum fuzziness, even though the light itself is basically frozen.
Exactly. And the calculations actually show that this fuzziness is enough to preserve the important parts of black hole thermodynamics, even in this limit. It's pretty cool how quantum mechanics can defy those classical intuitions.
Now, I know from the papers that these calculations involve something called boundary terms, too. Can you explain why those are so important?
Think of boundary terms like setting the rules for how the system acts at its edges. Imagine drawing a circle on a piece of paper. The boundary term is basically defining what happens at the edge of that circle.
So in this case, the boundary terms are saying how gravity behaves at the edge of this simplified 2D universe.
Right. And they're really important for making sure the theory makes sense and is consistent. They keep things from getting weird or unphysical at the edges of space-time.
Like setting up guardrails to make sure everything stays on track.
Yeah, good analogy. The boundary terms keep the theory from going off the rails, so to speak.
Okay, so we've got our path integral, boundary terms, and a whole lot of complicated math, but what it all boils down to is this. Black hole thermodynamics still works in tandem gravity, even when the speed of light is gone. That's pretty amazing, right?
It really is. It suggests that the idea of a black hole, defined by its thermodynamic properties, is more robust and fundamental than we thought.
But I'm guessing it's not all smooth sailing. There must be some tough challenges when working in tandem gravity, right?
You're right, tandem gravity has some unique challenges, and one of the biggest has to do with something called negative specific heat. It's a weird thing about black holes that can actually make things thermodynamically unstable.
Oh, that sounds interesting. Let's dig into those challenges next and see how researchers are trying to overcome them. So we've been exploring this tandem gravity world, and it's been quite a trip. Before we went on that little break, we were just about to get into some of the challenges that come up when we're talking about black holes and their weird thermodynamics. You mentioned this negative specific heat thing. What is that exactly, and why does it cause so many problems?
Yeah, negative specific heat, it's a pretty counterintuitive idea.
Uh-huh.
I mean, usually when you add heat to something, it gets hotter, right? But with black holes, it's the opposite. They lose energy and they actually get hotter.
So the more energy a black hole radiates away, the hotter it actually gets. That seems completely backwards.
It definitely goes against everything we experience in our daily lives, but it's a direct result of this strange relationship between a black hole's mass, its temperature, and its entropy. And it can cause some real issues when you're trying to study the thermodynamics of black holes in tandem gravity.
What kind of issues are we talking about? Does it like make the whole theory fall apart or something?
No, it doesn't break the theory itself. But it does make it really tough to define a stable thermodynamic system. Think about it. If a black hole gets hotter as it loses energy, it's going to radiate energy even faster, which makes it even hotter, and so on. It's like a runaway process.
Kind of like a cosmic snowball effect, but with heat instead of snow.
Exactly. And this instability makes it hard to study how black holes behave in tandem gravity using our normal thermodynamic tools.
So how do physicists get around this problem then? Is there a way to control this runaway heating?
There are a couple of ways. One way is to basically put the black hole in a box.
A box. Wait, like actually put it in a container.
Not a real box, but more of a theoretical one.
Hmm.
Imagine confining the black hole in a kind of cavity, a space with very specific boundary conditions. And this basically creates a thermal reservoir that can exchange energy with the black hole, which stops it from getting too hot.
So it's like we're giving the black hole a thermostat to keep its temperature in check?
Yeah, that's a good analogy. If we're careful about choosing those boundary conditions, we can create a stable thermodynamic system where the black hole can reach equilibrium with its surroundings.
Very clever. Are there any other ways to deal with this negative specific heat thing?
Another approach is to bring in something called a negative cosmological constant.
A negative cosmological constant. Isn't that something to do with the expansion of the universe? How does that relate to black holes?
I know it sounds strange, but a negative cosmological constant can actually help to stabilize black holes. It's like a kind of cosmic pressure that pushes back against that runaway heating effect.
It's like the universe itself is pushing back on the black hole, stopping it from going out of control.
That's it. And this connection between black hole thermodynamics and cosmology, it's one of the things that makes tandem gravity so fascinating. It suggests that there could be these really deep connections between the very big and the very small, between the fate of the entire universe and the behavior of these tiny black holes.
All right, you officially blew my mind. We've covered black holes, a vanishing speed of light, Euclidean path integrals, negative specific heat, and now even cosmology is in the mix. I'm starting to see why you said tandem gravity is just the beginning.
It really is. And one of the most exciting things about tandem gravity is that it could potentially connect all these different areas of physics that seem totally separate at first glance.
You mentioned earlier that there are other parts of the Bronstein cube to explore, like this Galilean tandem gravity. Can you tell us a bit more about that?
Galilean tandem gravity is like the opposite of tandem gravity. Instead of taking the speed of light down to zero, we crank it up to infinity.
Faster than the speed of light. Isn't that like a fundamental rule we can't break?
Well, in theoretical physics, we can play with these extreme ideas and see what happens. And in Galilean tandem gravity, we find another fascinating corner of that Bronstein cube, a place where time and space work in very different ways than we're used to.
It's like we're stepping into a whole new universe with its own unique set of rules.
You got it. And by studying these different limits, we can get a better understanding of how gravity works in all its different forms.
This is all mind-blowing. But before we wrap up, I have to ask, what about the practical side of all of this? Does tandem gravity have any impact on our everyday lives?
Right now, tandem gravity is mainly a theoretical idea. It's about pushing the limits of our knowledge and figuring out the fundamental nature of the universe. But we've seen time and time again that these abstract ideas can lead to amazing technological breakthroughs down the line.
So we're basically exploring uncharted territory here. We might not know what we'll find, but the journey itself is what's important.
That's a great way to put it. And who knows, maybe someday our understanding of tantum gravity will lead to new technologies that completely change the world, just like quantum mechanics led to computers and lasers and all that.
Well, I'm definitely excited to see where this all leads. A huge thank you to our expert for taking us on this incredible deep dive into tantum gravity. And to all our listeners out there, keep those minds curious because there's always more to discover in this vast and amazing universe of knowledge.